Hello, CIS27. In this video, I'm going to talk about Unit 10, activities, the assignments, and the lecture, which is covering Chapter 10 in our book. And in this chapter, we are going to talk about cryptography. So when you look at Canvas, you can look at the task. In this week, we are going to cover cryptography concepts. We're going to talk about symmetric, asymmetric, hashing, key stretching, obfuscation, and also PKI. And we are to read the chapter, view the videos, complete the assignment, and then complete Lab 10. In the next page, you will find the notes. I provided some additional link about sorting passwords, using encryption, different type of encryption software, along with providing some additional videos on passwords, PKI, and hashing passwords. So in the notes, we will begin with defining encryption. And encryption is a way that we would scramble the characters, so that way we would make the data that is readable into unreadable after ciphering. And encryption would use different type of algorithm. And with different type of encryption, we would have different key length. And so now in the objective of the encryption is, its goal is to provide integrity, confidentiality, and non-repudiation. In integrity, in that it would provide assurances that data has not been modified. And hashing would ensure us that the data would retain its integrity. So when the data is hashed, it would generate a hashing value, and that hashing value is then would be compared to make sure that if it's exact match. If it is an exact match, then the data has not been modified. If the hash value is different, then we would know that the integrity has been jeopardized. The second area that encryption provides is confidentiality. It gives us a way to ensure that the data is only going to be viewable and accessible by authorized user. So encryption allows us to protect the confidentiality of the data. And in the encryption, we would have two categories, the symmetric and asymmetric encryption. So symmetric encryption uses the same key to encrypt and decrypt. Asymmetric encryption uses two keys, public and private key. And this would be referring to PKI in that. And also in PKI, we would need to issue certificates, where you would then have to manage the certificate that you would issue through certificate authority. And for asymmetric encryption, anything encrypted with the public key can be decrypted with the matching private key. So in a cloud environment like AWS, we would see that in order to connect to certain instances on the cloud, we would need to use PKI, and it would use RSA, in that you would have a public key and a private key in order to access your instance. So you can use encryption for connectivity. You can also use encryption for data, data transfer, storage, etc. But in the PKI, anything that you would encrypt with the private key, you would then have to decrypt using a public key. So if you encrypt with the public key, then you would have to decrypt using the matching private key. And when we're looking at web traffic, in ciphering, when you do stream cipher, you would then have to encrypt one bit at a time, and therefore when the system receives it, it would have to decrypt one bit at a time. If you would implement block cipher, in that the data would then be encrypted as blocks or chunks, and then when it arrives, each of the block would then be decrypted using its proper key. So another way that we can also provide confidentiality is through Stiganography. And stiganography is just a way to hide data within other files. It could be embedded, it could be hidden throughout the actual file itself. And so in some way, we can also implement stiganography along with encryption to allow us to provide confidentiality of the data. Now, in certain system or certain scenario, we would see that digital signature would be used. And digital signature only allows us to provide authentication and non-repudiation and integrity in that it would have a timestamp showing that when the party has signed or digitally signed a specific file, and it would allow us to implement the authentication process to make sure that there is appropriate integrity process and that the proper authorized user is allowed to access that specific file. So it's slightly different than what you see with encryption, and digital signature really allows us to identify the appropriate person that needs to be able to access the file or authorize a certain type of file. So for MD5, MD5 is known as Message Digest 5, and this is a hash algorithm that's producing a 120-bit hash. It was created in 1992, and in 2004, there is vulnerability that has been discovered. MD5 is often used in email file storage, downloads, and executable files. And at the lowest level, for hashing, you can use MD5. It is not the best technology to implement. However, you would often see this MD5 is implemented when you download files. For example, if you need to download an ISO or an applications, often you would see website implementing MD5 because it's easy to implement. So in our assignment, we will begin with answering the question by referring to the notes in chapter 10. For number 1, it asks you to describe how encryption is used to provide confidentiality and integrity. Encryption is used to provide integrity in that it gives you assurance that the data has not been modified, and hashing ensures the data retains its integrity. Confidentiality ensures that data is only going to be viewable by authorized user, and with that we often implement an authentication method with encryption. So encryption protects the confidentiality of the data. And also, you would also find that encryption also provides non-repudiation in that it puts a timestamp on when that file was encrypted, when the key was generated. So there's no going back and saying that certain specific files were not encrypted by a certain user. In question 2, it asks you when should you use MD5. And for Message Digest 5, we can implement this for email, for files, for storage, for downloads, for executable files. And we know that vulnerabilities in MD5 exist, so it should not be used too often. We would then transition back to the notes, and then in the next section it talks about SHA or SHA. An insecure hash algorithm, which stands for SHA, this was created by NSA for SHA version 1. So SHA-1 was created by NSA along with SHA version 2 or SHA-2. The first initial version was version 0. It was not used. In version 1, what they did was they updated the version 0 for use, and it creates 160-bit hashes. In version 2 of SHA, it is an improvement of version 1, and that can be 256 bit, 512 bits, 224 bits, or 384 bits. In SHA version 3, NSA was not the entity that produced this version, and this is known as keyhack, and it is the same size as version 2. So we know that hashes is vulnerable in that it can be captured, it can be compared to a known good hash in order to determine the hash algorithm, and so therefore hashes is not 100% foolproof technology for implementation. Now, in our assignment, it asks you which version of SHA was created by NSA, and we know that version 1 of SHA and version 2 of SHA were created by the NSA. In the next question, that would relate to the HMAC portion of our note, and HMAC stands for Hash-Based Message Authentication Code. This is your fixed string of bits, very similar to MD5 and SHA version 1. It uses shared secret that is randomly generated for the sender and the receiver. And so in IPsec, which is used for virtual private network, and TLS, which is often implemented with your HTTPS, it uses a version of HMAC, and HMAC should be complemented with, or it should be used with hashes like MD5 or SHA version 1. So the process of HMAC in that the hash would then be generated from the sender system. If somewhere in between the system is being attacked, the attacker would insert the hash after modifying the message. So they would stuff the message with the inserted hash value. And the hash would then be, if the hash is created on the receiver system, the modified hashes would then be compared on the receiver system. If it's not the same, then we know that the hash has been jeopardized. So HMAC would create the same secret key, which is shared between the sender and the receiver. In the next step, the computer of the receiver would calculate the hash on the received message using the shared key. When it's compared with the that's received from the sender, if the hash is different, the message no longer has integrity. So that would be the entire process in the case that if the hash is jeopardized. So in the next question, it asks you what protocol uses HMAC. That will be IPsec, TLS, that would use the version of HMAC such as HMAC MD5 or HMAC SHA1. Next, we're going to talk about Ripemd, and Ripemd stands for Race Integrity Primitives Evaluation Message Digest. This is a hash function that's used for integrity. It's used as MD5, SHA, and HMAC. And Ripemd can generate 160-bit fixed size hashes. Other version can generate 128 bits, 256 bits, and 320 bits. And so when we look at hash files, one-way function that creates a string of character, and you can find different hash tools that are available online. So it would apply these functions and it would generate a string of characters which represents the hash value or hash files that would be for whatever that you are trying to utilize it with. It would not be able to, it's not reversible, and the hash will always remain the same no matter how many times you calculate it. So when you generate it for that same particular file, it would then still be calculated as the same. And the hash, in order to verify the hash, we would use that generated file or the value of that hash and be able to compare it. And depending on the type of technology that you use, as we talked about earlier, you would use some form of key or secret in order to generate the comparison or compare the value of what was sent and what was received. So if the hash stays the same, the comparison that there are no different in the values, when we calculate it, then that means that the hash has integrity. And in Windows environment and the many of the versions of operating system, your passwords are actually stored as hash. And when you did the lab and when you watched my illustration on how we would be able to crack the Windows-based password, you would see that we would have to specify the type of hash that's being used in the Windows environment. So your passwords are stored as hash, and in some cases where you would have applications, some applications can be used to generate the salt passwords with extra characters that store in them. So instead of just storing the hash for the actual password, it would add additional characters or stuff the characters into the actual hash, so that way it would look like it's a different hash in the storage. And this just allows us to elevate the protection of that hash a little bit more. However, again, right, we would know that hash is not going to give us 100% foolproof in the protection of our password. And salting the hashes of the password is one way. Another way is also to implement key stretching or key lengthening. This is a technique to just increase the strength of the stored password, so that way we would minimize the brute force of the password. So to really reduce the probability in the brute force, or just to give us a little bit more time, we can lengthen our key or stretch our key for that encrypted password. We can salt the passwords by adding random bits, which would require more complex computation. And we can apply something like PBKDF2, which is password-based key derivation function 2, which uses salts for at least 64 bits, and it uses pseudo-random bits that's stored elsewhere. So that would allow us another level of protection. And another way we can do this is we can implement Decrypt, which is based on Blowfish block cipher, which is used in Unix and Linux systems. That's used to protect the stored shadow password. So in Linux operating system or Unix-based operating system, the password is stored as shadow password files. And in order to protect the shadow password files, we would then implement encryption or cryptography technology, such as Blowfish block cipher, to protect those files. So going to question 5, it asks you, what is salt in hashing? And salt simply implies the adding of random data or bits to the input of the hash function to guarantee the unique output, which is the hash, even when the inputs are the same. Subsequently, the unique hash produced by adding the salt can protect us against different attack vectors, such as rainbow attacks, while slowing down dictionary attack and brute force attack. It does not mean that that would completely remove the risk of dictionary and brute force. It just requires resources and time. So in the rainbow attack, that would also reduce the risk in the rainbow attack. So salting in hashing allows us to elevate the security measure, especially when we're looking at hashing passwords. And in question 6 asks you what is salt in password. It is it's random data that's used in an additional input to a one-way function that hashes data, a password or a passphrase, and salts are used to safeguard passwords in storage. So because it would allow us to protect what is being stored, which is our passwords, which allows access to different systems or different areas of the systems. Question 7 asks us, what is bcrypt? And bcrypt is based on blowfish block cipher. As we mentioned before, in ciphering or encryption, we can cipher in stream or in block or chunks. So when we cipher in block, we can use the blowfish algorithm, which is the derivative of your bcrypt. And bcrypt is used in Linux or Unix system to protect your shadow password files. So how do you really determine the integrity of the message if the message has been jeopardized? We would need to calculate the hashes for comparison. And when it's compared, if it's different, then the message no longer has integrity. So in the notes starting on page 2, you would see some hash example and a table of different hash algorithm and the comparison. So in the example, we would have an application that calculates MD5 hash on the sender's computer. The hash is then sent to the receiver's computer. The hash is created on the receiver's computer of the same message. Then the hashes would then compare on the receiver's computer. If it's different, then the message has lost its integrity. So in the table, it gives you the overall view of MD5 SHA version 1, 2, and 3, HMAC MD5, and HMAC SHA 1. So now in the hashes, MD5 and SHA 1 through 3, we would see that there is hashing integrity. So that would check for the integrity using hash. And there are different bit size. With HMAC MD5 and SHA1, that is used to check integrity and authenticity in that it would implement authentication process with the hashing. So when we encrypt data, we have to consider the type of data that we're working with. The majority of our data could be in transit, it could be in use, or it could be at rest, depending. Now, encryption, you know that would take resources, computational power, time, and so on. So we have to evaluate the option in encryption and on what type of encryption algorithm that we would implement, what is it for, the purpose, and so on. So when we look at encrypting data, data at rest is what's considered stored data on media, like on your USB drive, your external hard drive, your internal hard drive, solid state drive. And commonly encrypted, we would only encrypt the sensitive data in storage. Things that would be essential to the company operation, that would have sensitive information, blueprints, design, etc. And fields holding the sensitive data. The areas that depending on the container that could be holding the sensitive data. So we would actually encrypt the container, and we would add the data into the container, and the data would then inherit the encryption attributes. For the data in transit, that will be data that's coming into your network and leaving your network. It will be sent over the network. And again, we would protect the sensitive data by encrypting the sensitive data or the session. So when we're looking at like money transfer, access to bank account, transactional type of session, purchases, etc., those type of sessions would then need to be encrypted. And so therefore you would see e-commerce website implementing HTTPS with using TLS. Data in use, that will be data that's being accessed by the system, and usually data in use is not encrypted. When we're finished using it, when we then would archive it or store it, then we would consider encryption, because if you encrypt data in use, it would take a lot of resources, so therefore it does not make sense to really encrypt and decrypt that way. So applications can be used to encrypt that store once we store the data, and then decrypt when the data needs to be used again. So the encryption elements, we have to look at two things. Number one, that will be your algorithm, which is a mathematical calculation of the data. That's always going to be the same. Two is going to be the key, the number or the value that provides the validity of the encryption. And the key also have length and bit size. Okay. And in some cryptography, as you can see, algorithm, it would use multiple keys, like what we talked about, like RSA or PKI type of encryption. And with encryption, the other areas that we would look at is how is it generating values? Is it going to be randomized, or is it pseudo-random numbers? Encryption sometimes require a random or pseudo-random. Pseudo-random just means that it appears to be random, but it's always going to produce the same output based on the number of input. So with that, we can see that how the algorithm would then be deterministic. And in a wireless-based type of environment, you also see it's very visible when you use Wireshark to scan traffic, and you can look at like wireless traffic where you would look at initiation vector. And this is just going to give us the starting value of the cryptographic algorithm. So the attacker, when they scan the traffic and they're able to identify the IV, that would give them some idea of what is the starting value for that particular algorithm. Nonce is the number that used once, and this is a seeding value that's used for randomization or pseudo-randomization. And another terminology that you often see is exclusive OR or XOR. And simply, this is a logical operation that used in some encryption scheme to compare two input. If they are the same, the output is true. If it's different, then the output is going to be false. So when we look at the next question in our assignment, it asks us to describe the encryption strategies for data at rest, data in transit, and data in use. So for data at rest, that will be your stored data on media. We would then encrypt the storage devices, the folders, the archive containers, and set up the actual files. So when we add the files into the container, the storage devices, it would then automatically be encrypted. Your data in transit, that would be data that would be sent over the network and encrypt, that would often be seen as web data, or so in that case we would use TLS in order to encrypt web data, and we would use SALT to for password hash, and we would use email encryption for email transfer. In data in use, that would be the data that's being accessed by the system. So we would not encrypt the file while it's in use. When it's complete, when we store it, then we would then encrypt the file that is stored. When we need to use it again, we would then decrypt the data. Now in Windows environment, for data, we would use NFS, and then when we use storage encryption, we would use BitLocker. And BitLocker is designed for just storage, the actual drive encryption, where when you use data encryption, then you would, if you format your system with NTFS, then you would be able to use NFS, which allows us to encrypt the actual data, the container, the folder, etc. So the differences between block and stream cipher, in that the block cipher encrypts the data in specific size block. It could be 64-bit or 128-bit block. And it would divide. So if you have a large file, it would take that file or the message and chunk it into blocks that would fit that specific block size, either 64-bit or 128-bit. Then it would encrypt each block separately, and this would be effective when used for file with or specific file size database field. Now in stream, we talked about how stream, that would be one at a time. So stream would be more efficient than block, and it would use when the data size is unknown. So when you're looking at web type, the stream data, it's coming in, you might not know specific size of that data, then you would then need to use stream cipher. And in stream cipher, it would then be sent continuously in stream over the network, and you should never reuse the key, because it should be only used once. Because if you reuse the key could be guessed, and that key could be used, because it's shared key, that same key could be used to encrypt or decrypt. Okay. So for 10, we specify the differences between the block and the stream cipher. Now, on the notes, it goes further into secret algorithm, that will be kept secret, and then diffusion and confusion. So confusion is that encryption should be significantly different than text. So when you look at the encryption elements, you need to look at different areas of or factor of that encryption. What is the level of confusion? And then diffusion ensure that the small changes in the plain text result in the large changes in the ciphertext. So you also want to look at diffusion factor for that encryption. Now, for the weak and depreciated algorithm, that means that those can be cracked, or flaws have been discovered in the algorithm. The high resilient algorithm, basically, it tells us that the security of the encryption or the encryption key is high in that it prevents the attacker from gaining information, or they're unable to achieve the cracking process for that encryption. Block and stream cipher, as we touch on this in the assignment, you can find this on page 3 of your notes. Next, we're going to talk about cipher modes. And for cipher modes, we would have electronic codebook, which is your ECB. This is the simplest mode in the operation. It divides the plain text into blocks, and then it encrypts each block using the same key. It doesn't, because it's using the same key, we don't recommend it for use today. The next cipher mode is cipher block chaining, your CBC. This mode is in some symmetric block cipher, and you hear a lot of block chaining when we're looking at cryptocurrency and so on. So now you know that it uses the cipher block chaining, which is a mode. And it uses IV for randomization when encrypting the first block. Then it combines the subsequent block with the previous block using exclusive OR operation. Each block encryption is dependent on the previous block. Now, the only downside of this is that it would be delayed. There's some latency with block chaining mode, and it's less efficient than other modes. The next mode is your counter or your CTM, and this mode converts your block cipher into stream cipher. It combines your initiation vector, your IV, with the counter, and it uses the result to encrypt each plain text block. Each block uses the same IV in combination of the counter value, resulting in different encryption key for each block. So you would then have each key for each block. They are different. And this would be then beneficial if you are using it on multiprocessor system for this mode, as it would require multi-blocks processing at the same time. So counter would require a lot of resources. Now, cipher block chaining does require resources, but there is some pipeline delay, and so it would then be less efficient. The next mode is going to be Gallows counter mode, or GCM, and this mode of operation is used with block cipher. It combines your CTM with the Gallows mode of authentication. So there's an elevated level with authentication. It does not authenticate the user of the system, but it'll provide the integrity or authenticity and the confidentiality in this particular mode. It also includes hashing techniques for integrity, and it's widely used as it is efficient. So we would see GCM being the preferred mode for cryptography if we're looking at efficiency. So in the 11th question, it asks you to select the cipher mode and explain your choice. So I chose counter, but you can also use your GCM. Your counter mode, your CTM, this one, as we explained earlier, the mode converts the block cipher into stream cipher, and each block uses the same initiation vector in the combination with the counter value. So as we know that we would have multiprocessors for in the case when we're looking at systems and servers, this can be implemented with the multiprocessor type of systems to process it multi-block at the same time. In the next part, we're going to talk about symmetric encryption. So earlier we mentioned that symmetric would use the same key to encrypt and to decrypt. So you would use the same exact key, and this key would then be shared. So secret key encryption or session key encryption, sometimes that will be referred to as symmetric encryption. So a type of encryption that you often see as symmetric encryption would be substitution cipher. And substitution cipher is different than shift cipher. In substitution cipher, we would replace the plain text with the ciphertext using a fixed system. So in an example here, if we're looking at the word PASS in plain text, we would then shift it 3-letter shift. That would be SDVV. And originated in the lowest level of the shift type of cipher you would see, or substitution cipher, that will be Caesar cipher. You would see the shift being implemented in the Caesar cipher, in that we would replace it, we would substitute the character with the character that shifted so many characters down in the alphabet. Now, ROT13, rotation 13, is a substitution algorithm. This was implemented for a long time, it was used for a long time, but it was later replaced by more sophisticated symmetric-based encryption, in that they found flaws with ROT13. So sophisticated symmetric encryption would have complex keys, such as your Advanced Encryption Standard, which is your AES. It uses 128-bit keys or 256-bit keys. So the example for this would be 2 servers that would send encrypted traffic back and forth using AES. The server 1 encrypts the data with a key, then send the key to server 2, which is then used to decrypt. Same key is not always used in encryption and decryption for some scenario, but keys are then could be changed multiple times throughout. But in the simplest level, we would then see it as the key is then sent from one system to the next in order to go from encryption to decryption. And AES, Advanced Encryption Standard, encrypts data in 128-bit blocks. It is a block-based cipher. Now, NIST adopted Ringedale encryption algorithm, the best, which is to remain within the top 15 for the algorithm. The key sizes for AES would be 128, 192, or 256 bits. You often see 128 bits and 256-bit length key is being used. This encryption is fast. It requires a 1 pass with to encrypt and decrypt. So when you go from encryption to decrypt, it's only 1 pass, whereas some other algorithm will require more than 1 pass. It is efficient, it requires less resources, it's best for small devices like your smartphones, tablets, etc., IoT devices. It is strong and it provides high level of confidentiality. So this is what you see implemented for a lot of mobile-based devices. DES is also another symmetric block cipher. It encrypts 60-bit block. It uses small key, such as 56 bits. This can be broken using brute force. It's not recommended for use today. Triple DES, symmetric block cipher, that was an improved version of DES. It requires 3 passes using multiple keys. So each pass would require each key going from encryption to decryption. It encrypts data at 64-bit block. It is not used as often as AES, but is suitable as an alternative. So the size for this would be 56-bit, 112 bits, and 168 bits. Next is your RC4, which is invented by Ron Rivas. And RC stands for Ron's code, and 4 is the version. Bronze code or Rivet cipher is also known as RC4. It is also called ARC4. This is using symmetric stream cipher. Unlike the other ones, they are block cipher. This is a stream cipher, and you can generate between 40 to 2048 bits. Again, and we talked about how stream cipher is when we don't have a certain known size for our data. So this is often being implemented for web, like HTTPS, used for HTTPS, secure socket layer SSL, or TLS connections. In 2013, NSA was able to break RC4. Later on, all vendors suggested that we would then implement AES as a replacement. Next, we're going to talk about blowfish and twofish. So blowfish and twofish are symmetric block cipher. It is strong and it would be used today. They are 64-bit block and support two key sizes length at 32-bit and 448 bits. Was invented by Bruce Schneier, designed blowfish to replace DES. It is faster than AES 256-bit. It encrypts data in 64-bit block, whereas AES encrypts data at 256-bit block. So the block size for AES is larger. Twofish encrypts data in 128-bit blocks, and it supports 128, 192, and 256-bit key length. It is one of the top 15 encryption algorithm. Aside from symmetric encryption, we need to talk about asymmetric encryption, which uses two keys in matched pair to encrypt and decrypt. And this is referred to as public key or PKI. So for public key encrypts the information, only the matching private key can decrypt, and the private key encrypts the information, then only the matching public key can decrypt. It is very strong, but it is very resource intensive. Key exchange uses symmetric to transport the key, so we would then encrypt the session for key exchange using symmetric encryption. So in the next question, we then be asked to select the type of encryption and explain the reason for your selection. I have selected AES, which is Advanced Encryption Standard. It encrypts data in 128-bit blocks. It is one of the best top 15 algorithm. The key sizes, the key length are longer, 128, 192, and 256 bits. It is fast. It only requires one pass going from encryption to decryption. It is efficient. It requires less resources, less computational resources, and it is best for small devices. It provides high level of confidentiality. Therefore, I selected AES, but you can choose any of the encryption as long as you provide your reasons. And we want to select the top 15 strong encryption algorithm. For 13, we're asked to differentiate between symmetric and asymmetric encryption. So for asymmetric encryption, it uses two keys in matched pair to encrypt and decrypt. Public key encrypts the information. Only the matching private key can decrypt the information. Private key encrypts the information. Only the matching public key decrypt the information. Very strong, but it's resource intensive, like we said. Key exchange uses symmetric to encryption to transport the key. Symmetric encryption uses the same key to encrypt and decrypt. It's also known as secret key encryption or session key encryption. It's used also for session key encryption. An example of this would be Substitution Cipher or Caesar Cipher. It replaces the plain text using a shifted fixed system. Same key is not always used to encrypt and decrypt. Keys can be changed multiple times throughout to elevate the security for it. So in the next part, I'm going to talk about certificate before we answer the rest of our exercises for the assignment. So certificate, this is implemented for key and authentication process. Certificate basically is a digital document that would include public key and information about the owner of that certificate. Now, in all the apps that you're using on your smartphone, and even in some secure website would require some form of certificate. The system would then have to either generate a certificate or it would then be receive a certificate by a certificate authority. So in most environment, you would have a CA or a certificate authority that issue and manage the certificate. We can put an expiration date on it where it would only be good for a certain amount of time. We can revoke a certificate where we would remove that for a certain system or even a certain user. So on the certificate, it would include serial number, issuer, validity date, subject, public key information, and usage information. And in Windows environment for the Windows Server operating system, you can enable CA as a role. And with that, you can manage the certificate as it would need to be distributed for different purposes for your organization. RSA is Ron Rivas, Adi Shamir, Lionel Alderman. This was developed in 1977. This is a very strong asymmetric encryption method. RSA is commonly used in a lot of different things today. It uses public and private key in the match pair. It's often used in the internet. It's used to establish system. A lot of vendors supports this. Like if you look at Raspberry Pi, if you look at switches, appliances, routers, etc., to connect to it, you would need to have RSA identity in order to establish, or even cloud environment. It uses algorithm that includes prime numbers to generate the keys, and the key size of this would reach about 2049 bits or even higher. Okay. Now, the main component for RSA is that it would rely on the difficulty in producing large prime number, so that way that would be its strength, is this area right here. So when we look at keys, we would then refer to different type of keys. We have the ephemeral keys, which is going to be short lifetime, and it can be recreated in every session. Or we would have static keys. The example of this would be Diffie-Hellman, which uses static keys and the ephemeral key. So this particular algorithm, Diffie-Hellman, uses both type of keys, and in some algorithm would use one or the other type of keys. Another algorithm would be your elliptic curve, which is your ECC. This one also doesn't require a lot of processing power. It would be best used with lower power devices or wireless devices. The equation formulates an elliptic curve and graphing points for the curve to create the keys. And next we're going to talk about Diffie-Hellman. And Diffie-Hellman is a key exchange algorithm used for shared symmetric key. It uses DHA, and it uses both type of keys, as we mentioned earlier, generate keys for each of the session. Stiganography is a way that we can hide data from plain sight, hiding data by manipulating the bits or embed the data, or we can hide data in white space and the file clusters, etc. So there are ways that we can hide the data. So for certifications, you need to know different type of encryption algorithm. You need to know the difference between asymmetric and symmetric. You need to know about stiganography. So a lot of the details that we go over in this particular chapter or unit is essential. And also digital signature. So digital signature would be used in email. It provides authentication, non-repudiation, and integrity, as we mentioned earlier. And for downgrade attack, that is a way for us to force the system to downgrade the security due to weak implementation of Cipher suite. So when we select the encryption, not all encryptions are the best encryption. We wanted to think about what are we using it for, because that will pertain to block or stream cipher, to the key length, whether it's resource heavy or it would be light on the resources for the, or it would require less computational power, and so on. So we would then think about how we would implement the encryption for different needs of the organization. So in the last part of the exercise, I want you to visit Openpgp, and PGP stands for pretty good privacy. Now, Symantec had bought the official license of the commercialized version of PGP, but there is Openpgp, and in the Openpgp, it is used mainly for email encryption standard. Okay, and so this is using with the proposed standard RFC 4880. It was originally derived from the PGP software, which was created by Phil Zimmerman. So what you need to do is you need to review this website, and you need to go through and answer each of the questions. What type of the operating system does Openpgp support? Okay. And for the second part, I want you to identify 1 to 2 Openpgp application for different type of platforms. So when we come here, we would then look at the operating system that it supports. So you can click more, and here it tells us that it supports Windows, Mac OS, iOS, Linux, and even browser-based type of email. Then we can select different type of applications for our platform. So in Windows, you would see these. And for Mac OS, you would see these. For Android, that would use Openpgp, that is, you would have these type, and then iOS and Linux and so on. So one of the common one that you would see implemented with Linux is Cleopatra. That's very common for email encryption. Okay. So then you would navigate through and you would select a 1 to 2 for each of the platform. Then once you do that, you can go revisit the website and you can read through and learn a little bit more about each of the type of application. And if it's browser based, you can have plugins for the browser, like for Outlook.com or Yahoo and so on. Okay. And if you wanted to know more about Openpgp, it talks a little bit more in extension about pretty good privacy here, and how the standard was defined when it was created and how it got changed over time. And then if you wanted to read the RFC standards, you can visit this, and this will take you to the RFC documentation. So now coming back to this, after you complete your assignment, you simply save your answer and then submit it onto Canvas. Thank you for watching my video. This concludes my lecture video for Unit 10. Please watch the lab video for additional instructions on the lab for encryption this week.